Hello! In this video, we are going to prove the following theorem. For all positive integers n, 1 plus 1 over n to the power of n is less than 3. Now, before we get into proving this theorem, we are going to prove the following lemma. For all positive integers n, 1 plus 1 over n to the power of n plus 1 is greater than or equal to 1 plus 1 over n plus 1 to the power of n plus 2. Now, to prove this lemma, we are going to use the following fact: Bernoulli's inequality. Suppose x is a real number greater than or equal to -1, and n is a positive integer. Then 1 plus x to the power of n is greater than or equal to 1 plus nx. Okay, so let's get into proving this lemma. Okay, well, since we're trying to prove a statement about all positive integers, let's give ourselves an arbitrary positive integer. I'll call it n. The whole goal is to show that this guy is greater than or equal to this guy. Now, we know that these guys are both positive. So to show that this inequality is true, we're actually going to show that the ratio of this guy to this guy is greater than or equal to 1. So let me actually write out the ratio of this guy to this guy. Now, inside this parentheses, this is just equal to n over n plus 1 over n, which is equal to n plus 1 over n. Similarly, inside this parentheses, this is just equal to n plus 1 over n plus 1 plus 1 over n plus 1. And that's just equal to n plus 2 over n plus 1. And now, from our properties of exponents, we can take this guy and move him into the numerator, as long as we swap n plus 2 and n plus 1. So this is what we get. Now, what we're going to do is we are going to multiply this times n plus 1 over n times n over n plus 1. Right, we're allowed to do this because we essentially just multiplied by 1. But now notice these two guys. We really have n plus 1 over n to the power of n plus 1 times n plus 1 over n. Well, that's just equal to n plus 1 over n to the power of n plus 2. And then, one of our properties of exponents says when we multiply these two guys, well, we essentially have something in the form a to the power of n times b to the power of n. Well, that's just equal to ab to the power of n. In other words, when we multiply these two together, we really have n plus 1 over n plus 2 times n plus 1 over n together raised to the power of n plus 2. Right, just like that. And actually, we can multiply these two fractions to obtain n plus 1 squared over n times n plus 2. Now, the next thing to notice here is inside this parentheses, the numerator is equal to n squared plus 2n plus 1. The denominator is equal to n squared plus 2n. Well, if we group these two guys together, we can read this as being n squared plus 2n over n squared plus 2n plus 1 over n squared plus 2n. Well, really, this is just equal to 1. So what we have in the parentheses here is just equal to 1 plus 1 over n times n plus 2. So now notice, we have something of the form 1 plus x to the power of n. So we're ready to apply Bernoulli's inequality. Yes, right? We all love Bernoulli's inequality. So we're going to take x to be, So we're going to take x to be 1 over n times n plus 2. and we're going to take n to be n plus 2. Well, 1 plus x to the power of n is precisely what we have here, so let me just write that out. And it's greater than or equal to 1 plus nx, where we took n to be n plus 2 and x to be 1 over n times n plus 2. So really, this guy is greater than or equal to 1 plus n plus 2 times 1 over n times n plus 2. From here, we see that the n plus 2's cancel out, and so this is just equal to 1 plus 1 over n. So what this tells us is that this guy is greater than or equal to 1 plus 1 over n, and therefore this entire thing is greater than or equal to 1 plus 1 over n times n over n plus 1. But then, if we distribute n over n plus 1 across this parentheses, we have that this is equal to 1 times n over n plus 1 plus 1 over n times n over n plus 1. Oh, really, that's just n over n plus 1 plus 1 over n plus 1. Adding these two fractions together, we get n plus 1 over n plus 1, which is just equal to 1. So, we have shown that the ratio of this guy to this guy is greater than or equal to 1. So if we take the inequality that this guy over this guy is greater than or equal to 1, and multiply what we have in the denominator to the other side, we obtain this inequality. And so, this proves the lemma. So what this lemma essentially tells us is that 1 plus 1 over 1 to the power of 2 is greater than or equal to 1 plus 1 over 2 to the power of 3, which is greater than or equal to 1 plus 1 over 3 to the power of 4, and so on and so forth. And another way of putting this is we have a sequence of real numbers, which is monotonically decreasing. And what that means is if we consider any term in the sequence, well then that term is greater than or equal to the term that comes after it. And a property of monotonically decreasing sequences that we can apply to this sequence is if we consider any two positive integers, say a and b. If a is less than or equal to b, then 1 plus 1 over a to the power of a plus 1 is greater than or equal to 1 plus 1 over b to the power of b plus 1. And so I said we were proving this lemma, but this is what we're actually going to be using in the proof of this theorem. Okay, so now let's get into proving this theorem. Well, since we're trying to prove a statement about all positive integers, let's give ourselves an arbitrary positive integer. I'll call it n. Now, I know one of two things is true. Either n is less than 5, or n is greater than or equal to 5. And in either case, we're going to show that this is true. Let's start with the case where n is less than 5. Now, in the case where n is less than 5, we really have a total of 4 possibilities, right? Either n is equal to 1, 2, 3, or 4. And, well, turns out, no matter which 4 of those we have, we can show that this guy is less than 3. Right? Because if we explicitly calculate this guy for n equals 1, n equals 2, n equals 3, and n equals 4, we have two 9/4, 64 27ths, and 625 256ths, which are all less than 3. So in the case where n is less than 5, we must have that 1 plus 1 over n to the power of n is less than 3. So this completes case 1. Now let's move on to case 2, where n is greater than or equal to 5. Well, let's explicitly write out 1 plus 1 over n to the power of n. Now, this is a positive number, and if we multiply a positive number by a number greater than 1, then we'll make the number bigger. So let's multiply this guy by 1 plus 1 over n, because 1 plus 1 over n is greater than 1. And we know that this is just equal to 1 plus 1 over n to the power of n plus 1. And now we can apply this fact. We're going to take a to be 5 and b to be n. Well, we know that 5 is less than or equal to n because that's the case we're working under. Because that is true, we must have that this is true in the case where a is equal to 5 and b is equal to n. So this is true. And therefore, this guy is less than or equal to 1 plus 1 over 5 to the power of 6. And okay, that's what it is. That was good. And we can check explicitly that this is equal to, and of course, this guy is less than 3. And so we have shown that 1 plus 1 over n to the power of n is less than 3. So in either case, we have shown that this is true. So no matter what positive integer n is, we have that this is true. So this proves the theorem. And so yeah, that's pretty much it for this video.